So question 3, part A of question 3 says the results of an investigation to ascertain the education levels of a sample of 200 adults are shown in the following table. So we have the education levels that we see here. We have the number of males in each category and the number of females in each category. We call this kind of table a contingency table. So if an individual is selected at random, so we are randomly selecting from these 200 adults, we need to find the probability of selecting these conditions. So generally in probability, so the probability of an event A, you would have the total of the desired outcomes over total possible outcomes. So in this case, we're looking for a person who has primary education. So a person, it could be male or female, who has primary education. So if we're looking for people that has primary education, if you look at this, the total number of people that have primary education would be 89. So that represents the total of the desired outcomes. We do not care if they're male or female. That is a person, so it could be either male or female. So therefore our total desired outcomes for primary education would be only 89. So we would have 89 and we will now have to put that over the total possible outcomes. Now when we are talking about the total possible outcomes in this instance, we are talking about the number of people we are choosing from. So remember, we're choosing from 200 adults. So from 200 adults, there's a chance of us picking 89 people who had primary education. So therefore, the probability would be 89, which is the desired outcome. So in this case, having primary education over the total number of adults that we can choose from, which would be 200. So number 2, it says a woman given that she has tertiary education. So what we call this here is conditional. It's a conditional scenario. Okay, so I'll show you 2 ways to do this. I'll show you a straightforward way when we're using contingency tables. Then I'll show you the way we can calculate it using standard probability rules for conditional probability. So a woman, given that she has tertiary education. In order for us to do this, I'm just concerned about looking at those who have tertiary education. So if I'm looking for those who have tertiary education, in this case, that would be 48. So that's the total number of people who have tertiary education. In this context, we're only looking at the people who have tertiary education. How do I know that? Because it says given. When it says given, I know that we're referring to that specific group. So in this case, we are referring to the tertiary education group, which has 48 people. So there's only 48 people that do tertiary education. So that's the group that we're looking at. So imagine we have 3 different groups here. So one is for primary, one is for secondary, and one is for tertiary. What we're saying is, let's go specifically to the tertiary group. So we're going inside the tertiary group. I'll think of it like a classroom, which has 48 people inside of this. So this entire section is 48. And the only thing we care to look for in that classroom would be who? The women. We care only about the women inside of this group. So the total possible outcomes that we can have here would be 48. But how many women do we expect to see inside that class, which is a tertiary class? Now, when you look at this, we have female 20. So therefore, we can say that in that class we have 20, therefore it's 20 out of 48. So just to put it into context, imagine we had this here. The males that make up this class would be 28 and the females would be 20. So together they make up 48, but we are looking specifically into that group because of that given situation. Alright, so in our next scenario, it says a person with secondary education given. This word is always a segue into the fact that we have a conditional probability. So this again is conditional. So a person with secondary education. So this time the group that we are looking at would be who? So with this one now, we are trying to see which one. A person with secondary education. So we're looking for a person with secondary education given that the person is male. So we are focusing now on which group. They told us a condition. We're looking for a person given that the person is a male, right? So we're looking in the male section. So we have 105 males. So it's like we're asking, how many males had secondary education as a highest level of education. So in order to do that, it would only make sense to look for the males. We have 105 males. Now we need to see how many of those males had secondary education. So if you look at it, we have secondary education here, which would be 33 males out of 105. So therefore, my answer for this would be 33 out of 105. Now, using the same analogy that we used earlier, we're looking for a particular group, but this time we have two groups that it can be in. We can either have male group or the female group. Now, what we're saying is, in both of these groups, we have people who have primary, secondary, and tertiary levels of education, but we are looking specifically in the male group. Now, inside the male group, we have primary education. Someone else may have tertiary, and someone else has secondary. So when we look in the male groups, how many people have secondary education? 33. How many have primary? 44. How many have tertiary? 28. So what happens here is that we're looking at these specific values here, and they come together to give us a grand total of 105. Now, if we're looking specifically for the person who has secondary education that is male, we look at this. So there are 3 people in here, and they are male. 105. Now, just a reminder, this given makes it conditional, which allows us to not look at the females who studied secondary right now. We're just focusing on the males. So this is what this condition allows us to do. Alright, so I said that I would have showed you as well if we had to use it doing a formula. So I'll use the same concept. So part 2, we're doing the same question to show how we would have gotten this answer. So we know it's a conditional situation. So if we know it's a conditional, it's usually written like this. P, W, and we have this vertical line, and then we put here T. So it says a woman given that she has tertiary education. That means woman given that she has tertiary education. Now the formula for this is W intersecting T, probability of W intersecting T over the probability of T. At the bottom, we always put the condition down here. So bearing this in mind, what is the probability of selecting a woman who does tertiary? What is the probability of selecting a woman who had a tertiary level of education? So we're looking for a female who has a level of tertiary education. So as you can see here, it would be 20. But remember, in this context, we're looking at the overall, because we're just looking for a woman who has tertiary education, not in a specific group, but just in general. So that would be 20 out of the total number of people. So if we go to this random pool of people, both males and females, and we're picking someone randomly, the chances of us selecting a woman that has tertiary education would be 20 out of 200, because we have 20 women who have tertiary education, and the total possible selections we could have made out of the entire group was 200. So if we randomly selecting from this group, it's 200 people we can select from. So now the probability of a tertiary education. So how many people had a tertiary education? As you can see here, it's 48. So it would be 48 over 200. So using this formula, we would have this now divided by this. So we'd have 20 over 200, and we're dividing it by 48 over 200. Now where did I get this division part? That's just this line here. So this here divided by this. So if you know fractions, this will stay, this will turn to multiplication, this would flip. So then we'll be left with these 200s cancelling off, and we'll have 20 over 48. So this would have been if you were interested in using the formula to work out a question. So similarly, if we're looking at question 3 in that same formula approach, we would have said that a person with secondary education, so probability of secondary education given that the person is male. Okay, so likewise, same concept, S intersecting M divided by the probability of, you got it, this piece here. Remember, that always goes at the bottom. Now, what's the probability of selecting a secondary student? What's the probability of selecting someone who had secondary education and they are male? So that would be 33. So we could have 33 over 200. That's the probability of this first part. And then we would have that divided by, okay, the probability of males. So we have a male here, 105 out of 200. So this time I didn't go through the whole equating this to that and so forth. I just showed you that before, so it's the same principle. I'm just showing you this in case you wanted a different approach to answering the same question. Personally, I prefer using this approach because it's easier, quicker, more efficient. But if you're a structured person who enjoy using formulas and prefer to use a formula, this is the way you go about doing it. So then we have 33 over 200 times 200 over 105. So the 200 will cancel out and we'll be left with 33 over 105, similar to what we got here. So the last part of this question, it says determine if secondary education is independent of gender. So we have two genders here to consider. We have male and female. So we're not going to look at it from the totality perspective of just gender in general, because if you try to do that, it's everyone that we're looking at. So there's nothing to compare. So we have to split it and have males compared with secondary and then females compared with secondary. So looking at the male perspective first, now there's something that we need to know. If we have a probability of an event A, so this is what's common between them, we can say that this is equal to probability of event A times the probability of event B when A and B are independent. Okay, so just to emphasize something here, the only time we use this as a formula is if you're told in a question that it's independent. This is the only time you should use that, if you're told that it's independent. Otherwise, this is just something to prove. Okay, so basically in this instance now, this is how we're gonna test for independence. Now, since we're looking at gender, let's look at the males first. So we're looking for independence between secondary education and males. So let's start off with that. What is the probability of us having a secondary education with the people that we have here? So the total for secondary education would be 63. So therefore that would be 63 over 200. Now what about the probability of a male? So the probability of a male would be 105 out of 200. So the next thing we need to look at now is the probability of having a secondary education and being male. So when you look for secondary education and being male, we have 33. So now we're going to select this 33 out of the 200 people again. So 33 out of 200. So what we need to do to test for independence, we need to multiply S and M like we have here and see if it gives us the same answer as 33 over 200. So let's try it out. So PS times PM, so that would be 63 over 200 times 105 over 200. Once we work that out, we get 1323 over 8,000. Now this is it in its lowest form. You can put this in your calculator, especially if you have a fractions calculator, and this would be the lowest form, which is not equal to this. Just to save, let's represent it as a decimal so you can see the comparison. So in this case, that would be 0.165375. And in this case, now 33 divided by 200 is 0.165. So in this context, they are very, very close. They're very, very, very close. But if I'm being very strict about it, they're still not equal to each other. If we're looking at it from 3 decimal places, we can say they're approximately the same, which would mean that they are independent. But in this case, if I'm being strict about it, I'll say that because this is not equal, I know that they are not independent. Okay, it's very, very close, but as I'm saying, I'm looking for the exact value. I want this and this number to be the exact same value. So therefore I would say when it comes to males, there's no independence. Now let's check it out for the females now. So using the same situations, so we say that secondary education is 63 over 200. So in this context, the probability of females would be 95. So we will have 95 here. And the probability of selecting a female that has secondary education would be 30 out of 200. So therefore, we need to multiply S and F, the probability of those two, to see if we get 30 over 200. So in that case, PS times PF, so that would give us the 63 over 200 times 95 over 200. So this gives me lowest fraction of this, which boils down to 0.149625. Now, if we compare that to the 30 over 200, it's not the 30 over 200. We see that this here is 0.15. Now, as stated, if we were told to do it through a specific number of decimal places, probably could have considered that this is actually close to this and that education level is independent of gender. But because I'm being strict about it in terms of values, as I would like it to be the exact same value, I can say that in this case, they are not independent. So secondary education is not independent of gender. However, it's very, very close. So as it relates to these questions here, as you can see again, PS intersection F is not equal to PS times PF. My stance on this is not necessarily that the values are not close. They are close, okay? However, I want the exact value. So in this case, the fraction here that we have, I want these fractions to have been equal, but they're not. So 30 over 200 is not the same as 1197 over 8000. Likewise, in our other part, when we had 33 over 200, that's not the same as 1323 over 8000. So because they're not equal is why I would say that they are not independent of each other. But bearing in mind, if they told me specifically to use, for instance, 3 decimal places, then in that case, it's very much likely that they would have been the same values I would have gotten in N. But they did not say that. So I have to look at it from a perspective of exactness. So when I look at that, these values are not the exact. They are very, very close, as you can see here, but they are not exact. Same thing with what we had over here. It was 0.165 versus 0.165375, but they are not exact. Okay, so that's why I took this stance on this particular question. So with this one, it says a company manufactures 3 brands of vehicles. So we have vehicle A, B, and C. So the percentage of customers that purchases each of these vehicles is 35%, 50%, and 15% respectively. Given that a customer meets in an accident, the probability of the car being severely damaged is 0.6, 0.8, and 0.75 for vehicles A, B, and C respectively. So we have to determine the probability that a customer using one of the vehicles meets an accident where the car is severely damaged. So we want to look for the probability of obtaining vehicles that meet some accident where the car is severely damaged. Now the best approach to this question is putting this in a probability tree. But before that, let's just break down these values first. So I want to have all of these representing the same thing. So for instance, the probability of A, B, and C were given as 35%, 50%, and 15%. So this here represents the purchases. Now 35% is the same as 35 over 100. So if I divide 35 by 100, it will be 0.35. Likewise for this, it would be 50 over 100. If I do 50 divided by 100, I'm going to get 0.5. And for this, you can tell that it would be 0.15. The same concept of 15 divided by 100. Now, why did I do this? I want these to match with these values here. So when I actually do the question, I have values that are relative to each other in terms of what they represent. So in this case, we're looking at decimals. So the best way to work this out is drawing a probability tree. So we have 3 options. The first option is buying vehicle A. Second option would be buying vehicle B. And next option would be vehicle C. We have vehicles A, B, and C. So let's just say for vehicle A, the probability of purchasing vehicle A would be 0.35. Now the probability of purchasing vehicle B would be 0.5. And then the probability of purchasing C would be 0.15. So based on this question, I'm assuming that they already purchased the car. So given that they already purchased the car is why I'm only looking at the perspective of them purchasing the car, which is this probability here. This is why I'm setting it up like this. And I'm not having like the probability of them purchasing then versus them not purchasing. I'm already going on the premise that the vehicle was purchased and we're looking at what happens when they do get in an accident after purchasing these cars. So that's just me clarifying why I'm only doing that perspective here as opposed to splitting it as 0.35 for purchasing A and then 0.65 for not purchasing A. Okay, so now since they've purchased A already, we want to see what happens after as it relates to damages. So for the first one, let's say that this here is severely damaged and then we'll have not severely damaged. So we'll do that for each one. So severely damaged, then not severely damaged. Again for C, severely damaged, not severely damaged. So just to add a little visual representation of severely, we'll just say that this is what severely is. It's no longer able to use, just damaged, not severely damaged. Now, the question asks us to determine the probability that a customer using one of the vehicles, so it could either be A, or B, or C. They end up in an accident and the car is severely damaged. So then on this case now, for vehicle A, we could say that severely would be 0.6. For B, it would be 0.8. And for C, it would be 0.75. So I could put that here, 0.6. Here would be 0.8. This here would be 0.75. So therefore, we have 0.6, 0.8, 0.75. So not severely would turn out to be just one, take away this. So if I do 1 subtract 0.75, I'll get 0.25. If I do 1 take away 0.8, I'm gonna get 0.2. Now, just in case you're wondering how I'm doing this, essentially these two need to add up to 1, these need to add up to 1, these need to add up to 1, and in this case all of these add up to 1. So that is because when it comes to probability, the highest value that you can get is 1. So because of that, I know if they give me the value for one event occurring, I could figure out for the next event, for the event not occurring, which in this instance both of them would have to add up to 1. So we're looking for severely damaged. So anything that has severely damaged is what I want. So I want this scenario, and that is for A. I want this scenario, and that is for B. And I also want this scenario, which is for C. So I have 3 different scenarios that could happen. I could have somebody purchasing A and then they get in an accident and it's severe. Someone for B and it's severe. Someone for C and it's severe. So it's either A or B or C in that scenario that you can get. So if I'm doing the first one for A, I would end up with 0.35 and 0.6 because I'm looking at it from the perspective of purchased A and severely damaged. The other option that I could have, which would be R, for B, it would be 0.5 multiplied by 0.8. Why? It's B and severely damaged. Now the next one, C. I have to add that as well because that is the other option. So it's going to be 0.15 and severely damaged, which is going to give me 0.75. So we could work out these individual values, then add them up together. So this here would give me 0.21. So it would give me 0.4. And this would give me 0.1125. For my final answer, I just add these up. 0.21 plus 0.4 plus 0.25. So together, this gives me 0.7225. So my final answer is this. Okay, so I looked for the situation where all severe accidents occurred, which would be this or this or this. Alright, so for this first one, we want to calculate the value of A. This here is a continuous random variable, which has a probability density function, as we can see here. So before I answer this question, what I'll do is I'll actually do question 2. So you can visualize what this is supposed to look like, and then we'll continue from there. So these are 2 different functions that come together to form one function. So if I'm looking at the first one now, we have 0 going straight to 1, okay? So x is more than 0 but less than or equal to 1, but then it continues from 1 straight on to 2.5. So we're going to actually use 0 as our benchmark for the first value. So then I could say if we have this particular function fx, which is equal to x over 2, when x is equal to 0, the function, we'll use that as an input. 0 is equal to 0 over 2. So that's going to give me 0 for this value. So with the x value being this, and you can basically say this is y, if we were to plot it, we would have a coordinate of 0, 0. The next thing we have here now is when it's 1. So let's see what it looks like when it's 1. So when we have 1 as an input, it's going to be 1 over 2. So when x is equal to 1, that's what we get, 1 over 2. So we could do the same thing and say, well, basically this is our coordinate. So our coordinate would be 1 to a half. If I was to start to sketch that, I know that we have a value here of 0. I know at least here is 1. Maybe here is about 2. I know somewhere here would be like 3. So 2.5 would match around here, right? Now on the y-axis, We start with 0, and then after we have a coordinate that goes up to at least a half. Let's say up here was a half. So for the first part, or this section here, x over 2, I'm going to put my coordinates that I have. So 0, 0, as well as 1 half. So 1 and then half. So then that's my first part. Now, the fact that this is k remains the same throughout this entire value. So if k was a half, it will remain a half from 1 straight to 2.5. Obviously, since two of these are connected graphs, we know that it continues from this point here. So it continues along this straight line here, remaining constant, straight up until 2.5. So let me stop it right here. It's going to stop like somewhere about here. So I could take out this piece here. So the area underneath here should be 1. They say it's 0 otherwise, so then I'd expect a solid line to match with 0 otherwise for this part here. So this represents otherwise. Going down this way would be otherwise as well. So in this case, this would be the x over 2 part, and here would be the k part. Okay, so based on that, kind of know already what the value of k is. One important thing I must mention is that the area under a graph is equal to 1 when it comes to probability. So the entire area is equal to 1, which is going to be my premise for answering the other question. Now, I use that diagram to determine that k is equal to a half because, as I said, k will continue from where this graph ends, and this x over 2 graph, which is this line, ends right here, and k begins here. So this full line here is k, so I know therefore k is equal to a half. Now if I needed to solve this using calculations, all I need to do is prove that they are simultaneous equations. So remember, this is a y-axis. They intersect where? They intersect at this point, okay, when x is equal to 1. So that's a point where they both cross paths because of the value when x is 1. So just put it into theory. Let's just say fx was actually equal to y. So then I could say y is equal to x over 2. And another equation is y is equal to k. Now the question is, when are two of these equal to each other? They equal to each other when they intersect. So when they intersect, y is the same as y. So therefore, in this case, it would be x over 2 is equal to k, because I'm saying that this y is equal to this y at the point where they intersect, which is x over 2 equal k. Now the thing is, this kind of shows us where they intersect for the value of x. So they intersect around when x is 1. So therefore, when x is equal to 1, I can substitute into this simultaneous equation that we have. So then we'll have 1 over 2, which is equal to k. So that's how we can do the calculations for that. I already drew this so you could see it visually and understand what it actually would have been. All right. So we have that part now. Now the next part we need to figure out would be the upper quartile. The upper quartile. So for part 3, I'm going to use my value here, the half. What I have to figure out here is where the value of the upper quartile would be. So we are looking along this x-axis. We need to find it along this x-axis. Now the question is, when would we find the upper quartile? So the upper quartile, lower quartile, and median, we usually find the median around the point where it's 0.5, where the probability is 0.5. And then for the upper quartile, it would be where it's equal to 0.75. And just in case they did the lower quartile, it would have been 0.25. So these are key values to have when you're thinking of the exam. So the first thing I want to do is figure out what is the area under this triangle. So if I could figure out this area under the triangle, I could have an idea of how close to 0.75 I am if I find up to 1. So let's just see what that would be. So if I was to sketch that separately, I would have this triangle here. So from 0 to 1 is about 1 unit. Okay, so 1 unit. And then the height, remember we said this is k, which is a half, would be a half. So the height of this is a half. So let's see what the area would be. So the area of a triangle is half base times perpendicular height. So in this case, it would be half multiplied by 1 times the height, which is a half. So this gives me a quarter, which is the same as 0.25. So we know that the area in this one here represents 0.25. So in that case, if we wanted the lower quartile would have actually been 1. So let's continue our calculations. We need to explore this rectangle. Which portion of this rectangle would give us an area of a half? So let's just draw this rectangle by itself now. So say we have this rectangle. Now, to figure out the distance from here to here, it's going to be 2.5 take away 1. So from here to here represents about 1.5. And the height would be 1 over 2, or let's just use 0.5 just for context. So this here is 0.5, which is the same as a half, because that's a height here. Okay, that's 0.5. Now, we are saying that we already know that this area is 0.25. Now, we need to get to this area now. We need to get to 0.75. So the area left to find would be 0.75 take away the 0.25, which is from this. So that would leave us with 0.5. So we need to figure out at which point would we get an area that's 0.5 here. So we're saying that somewhere along here would give us an area that equals 0.5. Who knows where it is? I don't know where it is. It doesn't mean that it's half of this. It just means that some value from here to here, which gives us a distance of x, would give us an area of 0.5. So in other words, if I was to think of this portion now as a separate rectangle, I would have the same height of 0.5 and the distance from here to here is x, but the area must equal to 0.5. I know it's a bit tricky because we have this value and this value mixed up, but think of area as rectangle length times width. So in this case, we say 0.5 times x, which would be length times width, is equal to 0.5. So in order to get x by itself, we need to divide both sides by 0.5. When we divide both sides, cancel out, so x is left with 0.5 divided by 0.5, which is 1. So the value of x is 1. So we are saying that the distance between here to here represents 1. In other words, measuring from 1, we just add the x that we found, the 1 that we found, because remember, we're just checking for this portion, which makes sense because the area of this now is length times width. So 1 from here, so 1 unit times 0.5 is 0.5. Anything times 1 is itself. So we are saying that from here to here, we need a unit of 1, right? Which takes us up to 2. So we are saying the area inside here is 0.5. And remember, we had the area from this triangle, which was what? 0.25, which gives us 0.75. So as a result of that, I know that my upper quartile would be equal to 2 right here. Then I can say upper quartile equal to 2. So the next part 4, we need to figure out a probability where x would fall from a half to 2. So if we was to take our sketch again, go straight up to 2.5. So we are looking for from a half, so right here should be a half because that's dead center between 0 and 1. So we want the area from here as well as from 2 to this area here. Now since I'm looking at that area, I already know what this one is. I already know what this one represents. This represents an area of, based on our last question, 0.5. So now I just need to figure out this little section here now. So if you look at it, since this is going half and this represents the part of the first function, which is here, we know that this value here is going to be a quarter. But just in case you had any concerns, so when it's a half, so in this case, half is more than 0 less than 1, we can put it in this function here. So it's going to be half divided by 2, and half of a half is a quarter. So that just shows you that here actually supposed to be a half. So the height of this is a half. Now, if we could figure out the area of inside here, then we can add it to this 0.5 and get our final answer. So that shape forms a trapezium. So the height of this is straight up to a half. And from here to here is a quarter. And from here to here, the perpendicular height is half to 1 is a half. Now for the area of a trapezium, what we do is we use half multiplied by a plus b, which represents the sum of the parallel lines, times the perpendicular height to those parallel lines, which in this case would be half. So we could say half plus a plus b. So if I call this a, it would be a quarter plus b. So a quarter plus a half. And we are multiplying that to the perpendicular height. So that would be a half again. Now, all of this we could put on our calculator. When we work that out, that will give us 3 out of 16. 3 out of 16. And we said that the other important area was 0.5. So that means the probability of this, since it's the area underneath here, is going to be 0.5. In other words, a half. So 0.5 or half plus 3 over 16. A half is the same as 8 over 16. All of this you can do in your calculator, which gives you 11 over 16. So 8 plus 3 is 11 over 16. So our answer for this is 11 over 16. Another way of doing this question is we could have found the area of this here and the area of this piece here, add them together, and then subtract it from 1. We would have gotten the same answer. Just to do that quickly, let's look at the area of this first one. So the first one here is gonna be a triangle like this. So from here to here is half, and the height is a quarter. So if we're using the same half base times height, we'll have half multiplied by a half, because that's a base, times a height, which is a quarter, which is going to give me 1 over 16. Now this piece here, 2 to 2.5 would be a half, and the height is what? A half. So based on this one, it would be a half times the height, which is also a half. Now area of a rectangle is length times width, so we would say half times half. In this case is a triangle, so half times half is a quarter. So we're saying that these sections in red represent 1 over 16 and 1 over a quarter. So let's add those together. 1 over 16 plus 1 over a quarter. If you put that in a calculator, we'll end up with 5 over 16. Now remember, that represents the red spot. Now to get the area of these two here together, what we would have to do is 1 subtract 5 over 16. And what's 1 subtract 5 over 16? Over here, the 1 subtract 5 over 16 would give us 11 over 16, which is the same thing as if we did it the other way around. Okay, so just remember that the area under these graphs add up to 1. That's very important. So just remember, I knew that everything here, the area under this entire region that encompasses this, the area must be equal to 1. Okay, so hopefully that makes sense and clarified question 3.